Okay, so sounds okay? All right. All right, my name is Heidi Poxon. I work for Cray, and I'm a member of the Programming Environments group. And today I wanted to talk about Reveal, one of the tools that we have available in our programming environment. This particular tool we designed to be able to help users add OpenMP to their programs. So as we introduced GPUs into our systems several years ago, in addition to users who have MPI programs that want to add OpenMP, we also thought that this would be a nice stepping stone to start with OpenMP and then move on to GPUs. So we found several uses for this. So today what I want to talk about is the capability of Reveal. The first thing is that our intent is to reduce the effort associated with adding OpenMP to an MPI program. So traditionally a lot of our customers have pure MPI programs and have added OpenMP to these applications when the MPI stops scaling. So the goal is to produce performance portable code. So even though we are using the Cray software stack and this tool that is provided by Cray, the ultimate end goal is OpenMP directives in your source code. So technically you could take this work that you've done and move it to other platforms. We also, through Reveal, offer the ability to gain insight into what the compiler has done to your program. So first of all, as I mentioned, many of our customers have MPI programs, and so we wanted to develop a way as their MPI programs scale and maybe the MPI starts leveling off, how do you actually start adding multiple programming models or a hybrid programming model to your application? So a couple of things that we look for with a pure MPI code when it potentially could be time to add OpenMP is when the code is network bound as you're scaling. As I mentioned, as MPI starts leveling off, or maybe if you have shared resource contention on a node, you may be able to alleviate some of this by adding OpenMP to your program. So the typical approach to adding OpenMP to an application is to first identify the loops that you want to parallelize. So if you have a many thousand or maybe a several million line application, sometimes that's difficult to do, to identify which particular loops you want to parallelize. The next step is to actually perform the parallel analysis and scoping. And that, depending on the size of the loop, can be a daunting project, and we'll show you some examples here in a moment. And then adding the OpenMP layer of parallelism, so building the directive in so that you can actually run the loop in parallel. And then in addition to that, one of the things that Reveal can help with is giving you some optimization feedback so that you can also go after vectorization within your loops. So as an example, this is a sample loop. It's a loop nest from a Fortran code. And in this particular example, I want to try and parallelize the outer loop, so the do J loop. So the first thing I do is I take a look at this particular loop, and I'm going to have to determine, is this a good loop to parallelize? What prevents me from parallelizing it? And then can I get any help with this? Because there are a lot of variables associated with this loop. I also notice that there's a couple of calls to some subroutines within this loop. And so I know that I need to track the behavior and the variables through those subroutines to be able to determine if I can run this loop in parallel. And as you can see now on the other side here, I've brought up that particular subroutine which makes calls to a bunch of other routines. And so as a user, this is a very tedious job to go through all of these subroutines and go through the path that this loop will execute through in order to analyze all the variables and the dependencies, or the potential dependencies. So the first question is this a good loop to parallelize? That's the very first thing. I don't want in a large application to just open my first file and try and parallelize my very first loop in that file because I may not get a performance gain when I'm done. So we invented an approach to be able to analyze the amount of work or estimate the amount of work in the loops in your application so that you can more quickly identify which particular key loops are useful to try and add OpenMP. So the way you do this on our system is you use a combination of the Cray compiler, the Cray performance tools, and then ultimately Reveal. So by using the Cray compiler, we've set up an experiment where you load the module to access the compiler, you load a module to access and implement this particular experiment for analyzing loops. You build your program with a Cray program library, which is a feature that we've added to our compiler so that it's basically a map with a lot of information about your application, and it allows us to communicate, the compiler can communicate information about that application to the performance tools or to Reveal. So you load these modules, you build your program, and you run it. An example of the type of information that you get after running your particular program with this experiment is a sorted list of loops where the top loops on the list are the key ones that you would want to parallelize or attempt to parallelize over the others. So relative to the loops in your application, the important or most important ones, the ones with the most work in them, bubble to the top. In addition to them being sorted, we also give you the trip count, and we give you the number of times that that particular loop was encountered in the execution of your program. We tell you which particular function the loop came from and the line number. And so you can see as an example here, I've got two loops, one loop at line 33, one at line 34. You've got the trip counts at 100 and 2500. So you can see by this that you have a nested loop. So now what I've done is I've got my loop estimates, my work estimates for my loop, and I've got my program library from the Cray compiler. And the next thing I do is I'm going to launch Reveal with that information. So when I do this, the first thing that the user sees is they see a navigation panel on the left-hand side where the timings or that rank of loops is listed. The stars for those loops indicate that those particular loops have enough work to justify starting OpenMP threads. If I click on one of these particular loops, I'm brought to the source code for that loop. And you can see there's some letters in this column here. If I hover over those letters, those are the loop mark. That's the loop mark information from our compiler listing. So it tells you basically that the compiler, for example, vectorized and unrolled this particular loop by 2. So you can quickly see what sort of optimizations were made. In addition, we also list messages from the compiler associated with that particular loop nest, and we color code them as positive and negative messages. And the good thing about that is the user can quickly identify what the compiler was able to do and what it was not able to do. Here, one of the things that happens when you try in complex codes is a loop may be accessed from more than one location within the program. And so if you click on this drop down, you can see all the instances that this particular loop was accessed from. And in the lower area here, you will get the callback or the traceback of that loop from main, and so of that instance. So if you want to see how all the different paths to this loop, what all the different paths to this loop are from main, you can quickly get that information as well. The next thing I want to do is I want to actually scope my loops. So there is a button here, and by default what we do is we select for the user the loops that have enough work to justify starting OpenMP. The user is free to choose to deselect or select additional loops. And then there is a batch scoping capability. So in this particular case, I have chosen to scope 26 loops. After the scoping is complete, what happens is, again, you've got your navigation, but now it's highlighted with red and green. And if you click on one of the particular loops, you can get some more information. Anything that's marked green is able to be parallelized as is, and we can help you insert a directive that you can insert into your source code, or that Reveal can insert into your source code. And that code should execute correctly. Anything that's marked red has issues. There are things that Reveal could not resolve, or things that may need to be done by the user in order to create a parallel or to make this loop parallel. So as an example here, if I click on this particular loop that's marked in red, the additional thing you get is information about what the issues are with scoping this. What are the issues with running this loop in parallel? And as we tried to scope the variables as shared or private to build a directive, what sort of issues did we run into? So you get a list of variables, and you get anything that we were able to scope correctly is already listed, and then anything that's not is flagged. And then we give you a reason as to why a particular variable we had an issue with scoping a particular variable. So in this case here, there's a variable name, and when we put an @ sign, we are trying to convey that that particular variable came from a function down the call chain in this loop, and the function was remap. And then it says there's a possible occurrence involving this particular object. And so the user gets the type of information at their fingertips as to why this particular loop cannot be executed in parallel as is. Another thing that we do is, as we list the variables, we may be able to scope a variable, but we will scope it with a warning. In this particular case, this variable is a reduction, but it's a shared reduction, and with OpenMP, that is something that has to be called out and protected. And so we will call out that this is a reduction with our directive, but also the user will have to do something to create a critical section or something such that the loop can execute correctly. So one of the things I showed you a Fortran example. The other thing is what happens with C and C++. As we have more aliasing, for example, with C++, one of the things that we did add is we added the ability to more aggressively scope a particular variable instead of just giving up, but flagging a warning. So in this particular case, I have a variable A. It's a scalar and it's scoped as shared, but I did flag a warning. We're saying that we're assuming there's no overlap with other objects. We actually weren't able to determine if there was an overlap, and that's something that the user is going to have to confirm or deny. So if you request more information about that particular note, what happens is then we will tell you that we're assuming that there's no overlap between these particular objects. So we call out the objects, again, that you need to go and look at that are associated with A that might have potential overlap. Finally, Reveal has the ability to insert a directive for you. So what we do is we create a comment and say that this directive was inserted by Reveal, so it's very easy to identify which particular directives in your source code were inserted by Reveal. The other thing that we do is we can build a directive whether or not the loop is ready to be parallelized. If it's not quite ready and there are some issues with particular variables, we will put them in an illegal clause, which we claim or which we tag as unresolved. And what this does is this clause is basically like a set of homework or your worksheet. And so you can take this now to your favorite editor and you have your list of variables that you have to track through this particular loop to resolve. So everything else that we could scope is already built into the directive, and so that this functions just, once these particular variables are resolved and any potential restructuring or changes are made such that the loop can be parallelized, then your directive is ready to go. So the user would, over time, move these particular variables into their appropriate scoping clause. So the next thing that we did, in addition to helping the user build directives, scoping loops, and doing the dependence analysis on loops in a batch environment, is to take it one step further. We also did an auto-parallelization. So what we did with this particular case is the user does the exact same thing as before. They collect their work the loop estimates, the work estimates, excuse me. They build their program, and they launch Reveal. Now the one thing is, next to the scoping button there's also this lightning bolt. So what happens if the user chooses this is everything that we have automatically selected, every loop that we automatically selected, because it has enough work to justify starting OpenMP threads, is scoped, is analyzed, the dependence analysis is performed, the variables are scoped. Any resulting loops that were clean, that had those green markers on them, that were ready to be parallelized with OpenMP directives, are automatically done so with virtual directives through the compile. We rebuild the binary for the user and deposit a rebuilt binary as if the user had already inserted OpenMP directives into their source code. So what this does is this gives you an experimental binary that you can run. So this is a quick way to say, is this going to make a difference in my code? I haven't changed a single line in my source code yet. I just want to see if there's any low-hanging fruit to get any OpenMP parallelism. And if so, if it runs well, then you just launch Reveal again and ask it to add those directives, and then you're good to go. So the result is OpenMP directives in your source code. The other capability that the tool has is the ability, let's say that I already added OpenMP directives in my source code, but now I'm getting wrong answers, and I don't know why. One of the things that we can do is we can actually analyze your OpenMP directives and determine if there's any mismatch from what we think could happen. What typically happens, in this particular case, I made a simple example. I've got a directive that I have inserted here, and I misscoped one of the variables. And you can see that Reveal called it out, saying, hey, variable n is marked as private, but that's not what we agree. We don't believe that that's the scoping from our analysis. So that is something that you can quickly look at. What typically happens in real applications is if somebody inserts directives and they're getting incorrect answers, the what Reveal comes up with unresolved, because it's a more tricky situation to scope that particular variable in the first place, so the user maybe overlooks something like overlap between other objects. But the benefit of Reveal is, even though it's unresolved, it tells you why, or gives you some indication as to why it's unresolved that might trigger something in your mind as to, oh, I should have really checked this. Maybe it was a shared reduction and I forgot to protect the variable or something. The other thing I want to call out here too is that you'll notice this particular loop can be parallelized here. It's green, it's marked green, and there's another loop below it. So loop at line 69 and at line 70. Adjacent loops, probably a nested loop. One of the things that we'll do is we'll put a caution flag in there. Even though this particular loop at line 70 could be parallelized, it actually is better, most likely, in most cases, to parallelize on the outer level. And so we tell you, even though we could put OpenMP directives here, we really recommend you moving them out to the outer level. So finally, the last thing, just to give you a little bit of additional information, as we have the compiler optimization information, let's say you've built your OpenMP directives, and now you want to look at, within the loop, you want to look at optimization opportunities such as vectorization. One of the things that you can do as well is you can get your listing of all of your loops by compiler messages. So you can find all the loops in your application that did not vectorize, and they also have time associated with them, so that you can find the ones that took the most time to execute, and those would most likely be the first ones that you want to take a look at. So that's basically an overview of the tool that hopefully helps reduce the amount of time that it takes to add OpenMP to your program. The other thing in addition to this is, even though it needs the Cray compiler and it's a Cray tool run on Cray systems, the goal or the ultimate end is OpenMP directives in your source code, and so it is portable and can be taken with you with your application wherever you go. With that, thank you.